Okay, Quicksort. So this is another divide and conquer algorithm. Well, you take an array and you break it into smaller and smaller pieces. And so you're taking a large problem and turning it into smaller problems. So the trick is how the division is done. Now we looked at merge sort, and there's a video on that. Merge sort just breaks the array into half and then reassembles the broken up pieces. So most of the work in merge sort is happening on the merge. All right. The division part is just a simple calculation. If you look at the code, in fact, we could do that. Where is it? On merge sort, finding the middle point is just this simple calculation. Then we call merge sort recursively. It comes back into itself and does this calculation over again. But then we do this merge, and that's most of the work is in the merge. There's the merge. It's a lot of work. But for quicksort, it's kind of the other way around. For quicksort, you do this partition first, then you call quicksort, which comes back in and does a partition again. So most of the work is in the partition. And the partition is not a simple calculation. It's this little loopy thing here. Okay, so they're similar. Merge sort and quicksort are similar. They're both recursive in this implementation. We're calling merge sort's calling itself twice, and then doing a merge. But most of the work is in the merge, and the division of the array in half is pretty simple. Whereas quicksort, it's recursive. It's calling itself twice, but most of the work is in the partition. All right, so here's a partition. Let me finish this array. So I've got 40, 20, 60, 80, 10, 70, 30, 50. All right, then what you do is you have a data element, the pivot, which is really just the first item. You don't really need this. So here's the pivot. Then you make two pointers. I'm going to call them pointers, or they're really indexes. So you have P1 and P2, and then the pivot. So the pivot's just the first item in the array, and then the pivot's the first item in the array, and then P1 is the next guy, and then P2 is the last guy. All right, then what you do in the pivot is you do these, you have an outside loop which stops the whole thing, and then inside you're moving P1 and you're moving P2. And then one of two things, either P1 and P2 have crossed each other or they haven't. If they have not crossed, then you swap P1 and P2, and if they have crossed, you swap PV with P2, or in this case I'm using F, the first item, PV, right? And you continue that until these guys cross. So you'll see in the hand execution here. So basically I'm moving P1 this way until I find something that's bigger than the pivot. So I'm moving P1 to the right, looking for an item that's bigger than the pivot. And I find it at 60, because 60 is bigger than 40, right? So I move P1 until I find something bigger than 40, and it stops there. Then I move P2, looking for something smaller than the pivot. So it goes to this position, and it finds 30, right? So 30 is smaller than 40. Okay, so you move P1, you move P2. They have not crossed each other yet, so you swap the values pointed at by P1 and P2. So you swap the 60 and the 30. Okay, so swap 60 and 30. So redraw this array. So I swap the 60 and the 30. So now I've got 30, 80, 10, 70, 60, 50. Pivot is still here. Okay. Now we continue. So P1's here. You're moving it this way, looking for something bigger than the pivot, bigger than 40, and you find it here. So P1 stops here because it found a value bigger than the pivot. 80 is bigger than 40. Likewise, P2 was here, and you move it to the right, looking for something smaller than the pivot. So it goes all the way down here, stops here because it finds the first number. Moving to the left, it finds the first number smaller than the pivot, so smaller than 40. Okay, then you swap. You swap 80 and 10. So 80 and 10, right? So I'll redraw this array like that. So the pivot's still here. The 20, the 30, the 10, the 80, the 70, 60, and the 50, and P2 was here, and P1 was here, right? And then we continue. So move P1 to the right, looking for something larger than the pivot, then move P2 to the left, looking for something smaller than the pivot. You continue to do that until they've crossed. And I think they're going to cross now. So now I move P1 to the P1 to the right, looking for something larger than the pivot, and I find it here at 80. And then I move P2 to the P2 to the left, looking for something smaller than the pivot. It finds the 10. Okay, P1 and P2 have crossed, which is what this loop is saying here. P1 and P2 have crossed, so now I swap the pivot with P2. So you swap 40 and 10. You swap what P2 points to with the pivot. So the 40 goes over here and the 10 goes over here. So the array looks like this now. 10, 20, 30, 40, 80, 70, 60, 50. And now here's the magic on this thing. 40 is done, right? 40 is done. Because what we essentially did is we took all the small items, we kind of scanned with P1, looking for big items, and scanned with P2 looking for the other way around. So you scan P1 looking for smaller items and P2 looking for bigger items, and then you moved the smaller items to the left and the bigger items to the right. So you moved all the items that were bigger than 40. We moved those to the right, and we took all the items that were smaller than 40 and we moved those to the left. So when we're done with this, 40 is done because everything on this side is smaller than 40 and everything on the other side is bigger than 40. That doesn't mean they're sorted, but they're bigger than 40 on this side and smaller than 40 on that side. So 40 is done, right? This 10, 20, 30 happens to be sorted. That's a coincidence, but the 10, 20, and 30 are still smaller than 40. And the 80, 70, 60, 50 are all bigger than 40. They're not sorted, but they're bigger than 40. So that means 40 is done, right? So we've basically divided the array into two subarrays, of one consisting of 10, 20, and 30, and one consisting of 80, 70, 60, and 50. And 40 is done. So this was our divide thing. This was called a partition, but this divides a large array into two smaller subarrays, and then these subarrays still need to be sorted. How would you like to sort these subarrays? Well, let's just do quicksort, right? So we would continue with quicksort on this subarray, and we would continue with quicksort on this subarray. All right, and then when they come back, this is all going to happen like recursively. And when it comes back, these guys on either side of 40 will be done. So that's a partition. Let's see. So we did a partition on this. If you want to kind of map this to the code, we did a partition on this set of numbers, which found m, the index m, which is 0, 1, 2, 3. It found m as 3. Basically, it found the final position of 40, and then it calls itself quicksort on 0, 1, and 2. Right? It calls quicksort on the first index, which is 0, and the middle -1. The middle is 3, which is what it found here with this partition. And so it calls the subarray from 0 to 2, basically. Quicksort gets called again from 0 to 2. And it does this similar process, but with a smaller array. And then that comes back, and this thing will be sorted, and then it calls 4, 5, 6, 7. It calls quicksort from middle +1, which is 4, to the last, which is 7. So it calls quicksort on this subarray, which goes off and does that sort, and then comes back. Okay, so another way. Let me see. What should I do? I think. Let me do a quicksort. Let me do another partition on this. So this is going to get. We're going to call quicksort on this guy. It'll come back into here from 4 to 7, and it'll do the first thing that'll happen is a partition will happen on that. So because I want to give you another example of a partition. So let's see what happens when I do. So here's the pivot. This is P1. This is P2. This has 80, 70, 60, and 50. So we're going to move this pivot to the P1. Sorry, we're going to move P1 to the right, looking for something bigger than the pivot. So it's going to move all the way to here, because it's not going to find anything. Then we're going to move P2 to the left, looking for something smaller than the pivot, and it's found it already. So P1 and P2 have crossed. That's our condition for finishing up here. And the finishing up operation is we swap the P2 with the pivot. So we swap 80 and 50, and the 80 is done. We swap, P2 and the pivot, and 80 is done. Right, 80 is in its final position. It's in the last position. So then we can call quicksort on this guy, and it'll find somebody in its final position, and with a subarray on either side. I guess I could keep doing that. So we're going to call quicksort again on this subarray. So we'll have 50 here, 70 here, and 60 here. This is the pivot. This is P1. This is P2. So first we move P1 to the right, looking for something bigger than the pivot, and we found it, so we stop. So this kind of just goes like that and stops. And this guy, P2, we're going to move to the left, looking for something smaller than the pivot. So it's going to move to here, smaller than or equal to the pivot, little implementation detail. So P1 and P2 have crossed, so we swap P2 and the pivot. So basically we swap 50 with 50, and 50's done. 50 is in its final position, and you would continue. You would call quicksort on this subarray, the 70 and the 60. There's a pivot. It's P1 and P2. You would move P1 to the right, looking for something bigger than the pivot, and it would fall off the end. And you'd move P2 to the left, looking for something smaller than the pivot, so it would stop. P1 and P2 have crossed, so you swap P2 and pivot again. So you're swapping 70 you're swapping P2 and pivot. So you're P2 and pivot, so you're swapping the 60 with the 70, P2 and pivot. And the 70 is done. And then you would call quicksort on this last guy, which is a trivial case. And so 60 is done. Okay, if you took the time to, on a big piece of paper, draw out all of these all the way down for every subarray. So the other thing you could probably do in a hand execution is you could maybe show the relative position of the rest of the array. You could leave it empty, but just show the little squares. That would probably be a good way to indicate what's happening here. I can do another thing. I could do one more, because what was happening here is these arrays are so small that we would get to the end condition right away where you swap the P2 and the pivot. But the way the algorithm works is you move P1, you move P2, you swap P1 and P2. Then you come back around, move P1, move P2, swap P1 and P2. You keep doing that until P1 and P2 cross, in which case you swap P2 and the pivot, and then that terminates the loop. Right? So it's move P1, move P2, swap. Move P1, move P2, swap. Move P1, move P2. Now that P1 and P2 will cross, then you swap P2 with the pivot. Right? Let me make up some numbers and see if I can make that happen. So let's say I had 7, 2, 3, 1, 5, 6, 9, 4. So this is the pivot. This is P1. This is P2. And we're doing the partition, which is most of the work here. So we're looking for, we move P1 until we find something bigger than the pivot. So it goes all the way down to here, right? Then we move P2 looking for something smaller than the pivot. And we found it. So we swap P1 and P2. So the 4 and the 9 get swapped. And I could redraw 7, 2, 3, 1, 5, 6, 4, 9. So the pivot's still here. Then so now we move P1 looking for something bigger than the pivot. So it moves to here, P1. And we take P2 and look for something smaller than the pivot. So it goes to here. And 4 is smaller than 7. So this P2 stops. So you move P1, then you move P2. But now P1 and P2 have crossed. P1 and P2 have crossed. Right? P1 crossed P2, which means you swap. So swap P2 and pivot, right? So now we swap these two guys. We put the 4 here and the 7 here, and this guy's done. I don't have an 8 in here, so that would be the final position of 7, right? Everything on this side is less than 7, right? All of these numbers are less than 7, and all of these numbers on the right are bigger than 7. So 7 is done. Okay, then you would sort the two subarrays. So I'll do it one more time. So pivot P1, P2. Move P1, looking for something bigger than the pivot. So we're looking for something bigger than 4, which is this 5. Then we move P2, looking for something smaller than the pivot, which is this 1. P1 and P2 have crossed. So we swap the 4 and the 1. So 4 is done because everything on this side is less than 4 and everything on this side is bigger than 4. So 4 is done. You'd continue that in that fashion. So once again, here P1 and P2 crossed right away, but typically, they would scoot. P1 would scoot, P2 would scoot, swap. P1 would scoot, P2 would scoot, swap. You keep doing that until they crossed, and then you would swap P2 with the pivot. But before that, you swap P1 and P2. That's that. I guess what I'd like you to do in the homework is draw the recursive trees. So let's do a small array. Let's see how that. So I'm going to do it on a small array, but I'd like you to use the big array that I'm giving you in the homework document. So we call Quicksort on the entire array, 0 to 3 in this case. It's going to do a partition, which is going to end up. I've posted this same document online, and so to save time, I think I'm just going to show you where the 10 ends up being the final position. So you're going to call Quicksort on 0 to 3. It's going to find this partition, and then it's going to call Quicksort on the left subarray, which is null. So it's going to call it on 0 to -1. It's going to call it on the left subarray, which is null. So this guy's going to return right away. Then it's going to call it on the right subarray, which is indexes 1 through 3. It's going to call it on the right subarray. Then that's going to locate this 40 in its final position. Kind of skipping the partition part and just looking at the recursive part. So 10 is done and 40 is done, and the recursive tree sort of looks like this, just abstractly. This call here that's doing this subarray finds the partition, then it does the left-hand side 1 to 2, then it does the right-hand side, which is 4 to 3, but there is no 4, but it's trying to do this null subarray, so this guy comes back right away, and the tree kind of looks like that, and this guy, if you drew the tree out again, the 1 to 2, which is not a null array, keeps on going, and it finds 10 was done before previously, the 40 was done before previously. It finds the 20, and it tries to sort what's on to the left of 20, which is a null, and then it tries to sort what's on the right side of this guy, which is 2 to 2. 2 to 2, and this guy tries to do the left and the right, which are null on either side of this guy, and the rest of this array, the rest of this this tree is still the same. So there's a document that's real similar to this that's already posted that has a little bit more detail, but what I'd like you to do is use the numbers I give you and show the quick sorts going all the way down, and then draw the corresponding trees as well. Okay, so it's a little bit of work, but it really is good stuff. It really makes you think about in detail how these algorithms work, and just sort of it's going to help improve your toolkit for thinking abstractly about large, complicated problems. So take some time, make it pretty. All right.